All right. Well, it looks like it is 3 o'clock and we're going to get rolling. You know, I always feel like we should have some kind of background music or something going on, so you guys have that to listen to while you're waiting for us to get started. I want to thank you guys for joining us, and I'm suspecting that people will join in as we get going here and get rolling, but we want to get started on time. We've got a lot of content to deliver for you and want to make sure we give everybody a chance to speak. If you are dialed in and just listening on audio, we do have visual webinar stuff going on as well. That maybe you're just dialed in to listen on purpose, and that's great and no problem at all. But just want to let you know that the invitation does have a link for our actual web presentation. So if you're just listening, I encourage you to call in and join us there as well. So let's get rolling. So we are going to be doing today the intro to OpenXLR8, FPGA design for the Arduino ecosystem, and glad you guys are here. First of all, what I want to do is do a little bit of a mea culpa here, a bit of a confession that when I set this up in the webinar software, I set up as a 60-minute webinar, but we have always done this as a 90-minute webinar, which is kind of what we're going to be on track for today as we deliver. Now, we've tried to tighten things up a little bit, and we don't want to unnecessarily delay, but I just want to let you know I feel bad about that, and I will take ownership of that change and that situation because I just made a mistake scheduling it. Hopefully, you guys can stick around. It doesn't cause too much trouble, but the team here is prepared for a 90-minute workshop. My email address is jason@loriumtech.com. You can send all your flames to me because the rest of the team had nothing to do with that mistake. So I just want to own that up front. Hopefully that doesn't cause people too much problems. So let's go ahead and talk a little bit about logistics. I think just about anybody here on the webinar has probably been on a webinar before. And so this is very likely to be not any kind of a surprise that how you can use these sessions. But in case you're new to Zoom, the way to communicate to us as we're doing this webinar today is click down below. There's a Q&A button on the bottom bar down there. And you can ask us your questions. We can answer those via text, or we can answer them live in terms of how we're talking. We'll see those notifications as we go along. And while one of us is talking, the rest of the team is going to be answering questions. When you click that button, you'll get a nice little box like this, answer your question, and we will get it answered as soon as we can. All right, so the team here today that's going to be talking to you, of course, there's 4 of us sitting here in the office. I'm Jason Pecor, and I'm responsible for sales and business development for Lorium Technology and on the marketing side. Steve Phillips and Brian Craker are our 2 lead engineers for XLR8 and for our boards. Steve on the hardware side and Brian on the software. They're going to be doing the bulk of the presentation today, so you'll be getting their expertise. And then Harley Judes is sitting right on the other side of the wall from me. She's our digital marketing specialist. She handles kind of the background logistics for the webinar, as well as a lot of our website, social media, and things like that. So got a great team behind us here as we are getting ready to deliver this presentation. Now, one of the things we're going to do today is we're not going to get too deep into our product in terms of talking about what they are, but I do want to introduce them so you have a feel for the products we offer. I think a number of you are already familiar with our products, but just in case we are new to you, we specialize in generating or creating a line of FPGA-based boards and development boards, so basically embeddable boards and development boards. And that really started with this XLR8 board, and this was the first one we came out with late 2015, early 2016. And that was followed up by the Snō Board, which went into production last year, and we started selling that in December. Nice, small, compact footprint. We just recently announced early this year our Hinge board. So Hinge is more of a wireless IoT sensor hub. It's got all kinds of connectivity on board, Ethernet, Wi-Fi, a bunch of other interfaces for connecting IoT sensors. And that is currently going into production. They're not available yet, but they will be this summer. We just made that announcement earlier this year. We're really excited about our Hinge board. We do have one other board that we call Snowmaker that doesn't have its own FPGA on it, but it's really designed to be sort of a breakout carrier board for our Snō Board. And that is one that we are producing currently, and you'll see those showing up on our distributors' websites here very soon. And we'll make an announcement as soon as that happens. So if you're interested in Snow, you like the form factor of the XLR8 board, you can take advantage of Snowmaker and kind of break that out for yourself. So what is it that makes our products unique, and why did we do this? Again, you may have heard this before, but real quickly, all of our boards are Arduino compatible, but they're FPGA based. And FPGA, of course, stands for Field Programmable Gate Array, essentially reprogrammable hardware that you can change the functionality of that hardware. If you look at Accelerate we designed originally to be a drop-in replacement for the Arduino Uno and give customers the ability to take their Uno-based design to the next level, or their Arduino-based design, whether it's another clone. This could just drop right in, but you take advantage of the FPGA benefits and use that in place of a standard Uno or a standard Uno clone. Now with Snō, it's a bit different, and that's what we're going to be kind of focusing on today. Or as I mentioned, if you saw one of our videos earlier this week, we're actually going to be doing the OpenXLR8 flow with one of our Snō boards, although it's same across all of our boards. But Snō makes a real nice embeddable system on a module, nice little dual inline FPGA module that you can use for your projects. All of our boards are based on the Max 10 FPGA by Intel, so formerly Altera. This one for Snō is a 16K LE device. It's the M16 version. For those of you who are familiar with this line, the Accelerate board has an M08, and our Hinge board has an M50. So that's a real big design. In fact, that's the biggest Max 10 that Intel makes on our Hinge board. One of the things that makes our boards unique is they are programmable with the Arduino IDE. And they're programmable in two ways. One is you can write your code, your sketches like you would for an Arduino board. You can actually put that onto the AVR microcontroller that we have on board these FPGAs that make them compatible. We've designed our own AVR compatible microcontroller. It works just like the Atmel 328 that's on the Uno and on other boards. So you can plug this in and it'll function just like an Arduino compatible board. You can also upload new FPGA images using Arduino as well. And we're going to talk a bit about that as it relates to the OpenXLR8 flow. We have some images that we ship right with our boards. You can get access to through the Arduino IDE, and you can update those images again using Arduino software, and you don't have to use Quartus or anything to just change the prepackaged images that we supply. But we're not going to be talking about that path here today. If you want to learn more about how that works or more about our boards, we have a truckload of videos out on our YouTube channel. And so you can learn more about how to use our FPGA images as part of Arduino, what some of our accelerator blocks that we ship and supply do. There's a lot of resources out there. We're not going to get into that as part of this presentation. This one, we're really going to focus on putting your custom logic onto the FPGA, making the assumption here that you have some familiarity already with Accelerate or Snō or those boards and how you can use them. So why FPGAs? I mean, one of the questions we get is, well, why would we do this? Why would we take FPGAs and try to target it toward first this Arduino kind of maker environment, but then onto some of these smaller boards? Why is this interesting to us? Well, we have a video series that we put together that's out on our YouTube channel that we've talked about. It was really based on a talk I did at IoT Fuse conference last year, but we just fundamentally believe in the power of FPGAs as it relates to the IoT or other applications where customers have started or companies have started by using an Arduino board or by using something similar, maybe a microcontroller, and they're bumping into performance issues and they want to be able to accelerate that performance. FPGAs are a great way to do that at a low level, and especially with smaller FPGAs like this Intel Max 10 that are designed for industrial uses. Great solution to be able to take some of those microcontroller problems and accelerate them. And it really comes down to performance, programmability, and security, the ability to offload functionality from software, run it in hardware, and the additional speed and performance that you get. Again, I'm not going to give you that whole speech today because it's something that we're really passionate about here. We think it's going to make a big difference in the IoT going forward. You can watch those videos, get our take on that. But we really wanted to bring that functionality to the Arduino space. And it's just such a ubiquitous platform. So many people are using it to get things started. It's a great entry point. If you are already an FPGA designer, using our boards then gives you, it's kind of the flip side of that, gives you access to that Arduino ecosystem, but you still have the ability to design your own custom logic. And so the way that works is if you look at a block diagram of our board, or of the chip that's on our boards, we've got our AVR compatible core that we've designed, along with some other logic to allow it to load the flash and things like that and reconfigure. But essentially, there's a chunk of that FPGA dedicated just to these custom accelerator blocks. And this is where that custom functionality goes. Now, in the case of things that we've designed, it's just already sitting on the FPGA when you buy your board from us. But if you're going to design your own, you will create your own accelerator block. Now, we use this term accelerator block, and what we mean by that, it's essentially an optimized hardware implementation of a specific function on the block. So call it an offload engine, call it an accelerator block, or an acceleration block, or just a custom logic block. But the idea here is that it's custom hardware implemented right on the FPGA very tightly integrated with the microcontroller. And all the XBs can access the same register space as the microcontroller. So it makes it very easy to use, very easy to integrate with your code. In terms of available XBs that we currently have and that we make available to you, there's floating point math, servo control, NeoPixels, or some of the very early ones that we did. We've got some communication interfaces like SPI, I2C, and UART, as well as a handful of other things that we've done, a lot of which are good to support robotics applications, motion control, things like that. So quadrature servo. We've got a new radio controller receiver interface. So if you want to use something in a drone platform or a robotics platform and talk to a receiver for an RC controller, you can do that. One of our engineers came up with an Accelerate Pong game. So if you want to play old school Pong on your Accelerate, you can do that with an XB. All right. So let's talk about OpenXLR8, because this is the flow we're going to talk about today, and this is how you get that custom functionality onto the board. Whether you want to use a Snō Board or Accelerate or Hinge, this is the methodology that we have come up with that allows you to take your custom logic, your custom HDL. In this case, right now, all of our stuff is designed in Verilog in terms of our core code, but Verilog or VHDL, run that through Quartus Prime for the synthesis. And then using Arduino, you can actually upload that to the FPGA. A couple of points about this. One is that you can use the free version of Quartus Prime, so Quartus Prime Lite, so you don't have to buy that tool. The Arduino tools obviously are free. And then the upload process, when you actually upload the FPGA, instead of needing USB Blast or any kind of JTAG programmer, you can go right through the serial connection that you have using Arduino. So again, that works with Snō, that works with our Accelerate board, that works with our Hinge board, and you can use those for any of the boards that we have. So this is the flow that we're going to talk about today, and the guys are going to walk you through. So at a very high level, here's what we're going to be looking at. We're going to start out by taking a look at talking a bit about the file directories, the directories that we have, or the files that we have that allow you to do this. Steve's going to talk a bit about that, how those things are sort of organized, and then we're going to start by taking a look at a low level at the LFSR block itself. And so that's the example we're using, right, is a linear feedback shift register, fairly simple design. It's very handy for doing things like random number generation. We're going to look at what the code looks like to implement this. First, actually take a look at what it would look like to do in software. And then Brian will show us what that looks like implemented in Verilog. And then taking a next step up, integrating that into the Accelerate wrapper that sort of transitions and gets all the IOs and data buses and stuff so that it can be used as part of the OpenXLR8 flow. We drop that into the OpenXLR8 top, and then finally integrate that into the Accelerate top. So we'll kind of step you through this process of what these files look like and what the code looks like and kind of what's changed. Now, for those of you who have seen this presentation before in the past or have looked at or maybe even used it, we have made some changes here, and this is an area where actually the team has done a lot of really great cleanup, added a lot of comments, and tried to make things as easy as possible to understand where things go. It's a lot of code to look at, and we don't necessarily expect you to understand it all the first time you see it, but it really has been documented very well to help you move down the field here if you want to use that. Then we're going to take that block, we're going to load it into Quartus and run it through synthesis, or show you how to do that. We probably won't chew up the actual time to do it, but show you how we'll go through that process and then how to convert the output to the right kind of programming file to get an RPD that we can upload into the FPGA. We'll go ahead, we'll actually upload that into the FPGA using Arduino. We'll show you how that works. And then finally, we're going to run the sketch that uses that code. So there's a little bit of discussion about the code that we need to write to access it, how we call that, and Brian will walk through that as well. And then we'll kind of get a chance to look at the benefits of it and how to take it from the software and the benefits you get by running it in hardware. So that is the 10,000-foot view of what we're going to do. I think at this point, I am going to stop talking and I'm going to let my colleagues kind of take it from here. So I'll stop sharing. And Steve or Brian, at this point, I will allow you guys to jump in and go ahead and get started. So I'll let you guys take it away.
Okay, thanks, Jason. This is Steve Phillips. I'm the lead designer for Accelerate. And we're going to walk through upfront some just detail on how we set things up, and then we'll go through the LFSR example. All right, so let's get started here. So there's two core libraries that are provided for OpenXLR8 that provide the foundation for running OpenXLR8 Flow: XLR8 Core and XLR8 Build Template. The XLR8 Core contains all the base libraries, scripts, source files that are needed to compile the entire FPGA design in Quartus. And then the Build Template provides a framework for the users to add their own custom logic. It's a template that you modify a few files here and there, and that allows you to bring in your own logic. To work within the Arduino IDE, we have to adhere to the library specification that they have. That leads to a file structure that's a little different than one might expect. Here we see, for an example lib, the files or directories that are required according to that specification. The examples and extras directories are optional directories. The source directory is where you would put all your C or C++ code, header files, that type of thing. And the library.properties and keywords.text files are used by the IDE to provide information about the library and to highlight keywords in the source code viewer. What we're going to do is use the extras directory, that optional directory, as a place to store the stuff that we need for OpenXLR8. Starting with the build template library, we can see the top level structure here. It looks very similar to that example lib from the previous slide. We've got the source directory, we've got the keywords text and the library properties files. We include a license and a README file here, but you can also see that we have this extras directory here, and in it we've defined 3 additional directories: the model sim, the Quartus, and the RTL directories. A little bit more detail on that, looking in the extras directory. The model sim directory there contains files that are used for simulation. The Quartus directory contains the files that are used when compiling it in Quartus. And you can see on the listing over on the right here, there's quite a bit more files there than I list here. That's because we support 3 different boards and 3 different clock rates. And so there's some multiplication here of files to support all those different combinations. And then in the RTL directory, we've got a few files there that are templates or support files for building the OpenXLR8. Just to highlight a couple of these files that are either going to be edited by us or are important to know about. For each board, there's a board top.qpf project file. That's what we'll load in when we actually start up Quartus. The OpenXLR8.qsf file contains the specific directives for Quartus for this particular implementation of OpenXLR8. Usually what that is specifying the Verilog source files that are used in the custom logic. Over in the RTL directory, we've got our OpenXLR8.v. This is the top level module of OpenXLR8. It's instantiated into the top level of the FPGA itself and provides the interface to that top level. The XB address pack is the file where we specify the configuration register addresses that we're going to be using within our custom logic. Those custom registers are determined by the user, but we need to assign addresses in the AVR address space in order to communicate with them. And the Accelerate Wrap template is a template file that we use to add the configuration data bus interface to the user's custom logic. And this is the bus that we use to communicate from the AVR core to the OpenXLR8 logic. The other library that's required is the Accelerate core. As I said, this contains all the libraries, IP blocks, source files that are needed for any of the OpenXLR8 implementations, a set of common files. And again, we're using that extras directory, and in there we've got a model sim Windows directory that contains files to support simulation. We've got a Quartus directory where we'll find QXP files, which are IP blocks precompiled live P blocks. We've got more Quartus settings files and synthesis files. And then in the RTL directory, we've got all the Verilog source code that's required to build the entire FPGA image. The methodology itself is 10 steps. What we first do is we copy our build template to accelerate build, because that's the location that the IDE is expecting to find the files. Now we're going to copy our unique RTL source files into the accelerate build extras RTL directory. Then we'll take our custom logic and wrap it with our accelerate wrap template, which adds the configuration register interface to our custom logic. Oftentimes we'll rename the accelerate wrap template something else at this point, because that's not really a good name once you've actually used it. Once we've got that wrapped, now we're going to instantiate that into our OpenXLR8.v, and this actually provides the interface directly to the core of the FPGA, the AVR core, the input and output pins, and inner logic. Next, we'll modify our XB address pack to add in our custom register address definitions so that the hardware will know which addresses we're locating our registers at. Moving over to the Quartus directory, we need to modify the OpenXLR8.qsf file to tell Quartus where to find our custom logic files that we're adding to this design. And at this point, we've got all our modifications done to the source files. So we'll launch Quartus and load our project file, the QPF file, for the board that we're targeting. Compile the design, and then convert that compiled design into the RPD format, which is what the IDE requires. And finally, we'll launch the Arduino IDE, and within the IDE itself, we'll run a program to load the new FPGA image directly onto the Accelerate board. So let's dive into the example that we have for the LFSR. I'm going to hand it off to Brian at this point to walk you through the next few slides.
As they're transitioning, what I want to do here as well is I have a quick question to ask, and I meant to do this right before Steve started talking. I do have a poll I want to launch just to get an idea from the people who are here what the level of experience is doing FPGA design. Is this something that's completely new? Have you used FPGAs before? That kind of thing. It kind of helps us get an idea, even as they're stepping through code and explaining some things. Getting a feel for people's experience there is useful to us. So if you guys can take just a second to take a look at that poll and answer, that would give us an idea as we're kind of taking the next step through the presentation stuff here. So it looks like we've got at least a kind of a good representation between, from beginner to expert. So it looks like just about everybody on the call right now has taken advantage or used them in some way. So that's great. Let me go ahead and close this so people can see it and share the results just so you guys all have an idea. So this is good. So thanks for everybody for replying to that. That gives us an idea here as we're stepping through. Appreciate that. All right, go ahead, Brian. It's all yours.
Great. Hey everybody, this is Brian Craker. I'm an engineer here at Lorium Technology. I'm responsible for library driver code for the different Accelerate modules that we have, and I'm responsible for the RTL for the LFSR module that we're going to be looking at today. So we're going to be building an LFSR module onto our FPGA on an Accelerate board, and as we do that, we're going to be taking our RTL code, compiling it with Quartus Prime, and using the Arduino IDE to load it onto an Accelerate board. So what that means is the two steps that a person would usually go through to build their own custom FPGA logic, we're going to be taking these two steps, and just as a shortcut, we're going to be building the LFSR module So I'm actually going to be taking this existing LFSR module that we've written previously and copying it to the XLR8 build directory and building it from there. So, so for anybody that's doing that, all that means is taking the XLR8 LFSR library that's available for free through the Arduino IDE, copying that folder and renaming it to XLR8 build. So an LFSR or linear feedback shift register, it's just a simple example that we're using. It's a way that you often use to generate pseudo-random numbers. And the particular LFSR that we're doing is just taking an 8-bit data register, and it's grabbing bits 7, 5, 4, and 3 of that data register, shifting the lower 7 bits up by 1, and then appending the result of the XNOR to the lowest bit of the LFSR. So the first thing we're going to do is look at the software implementation of the LFSR. So just quickly, I'm going to open up the Arduino IDE here. So this is the software LFSR example as you would build it in the Arduino IDE. So simple setup and loop in the Arduino sketch. This is the core of the LFSR logic here. So it's just grabbing those bits 7, 5, 4, and 3. And every second it's going to advance the LFSR. So I have an XLR8 board hooked up here on my side. So what I'm going to do is simply load the sketch to the XLR8 board, and then open up a serial monitor so that we can see the output of this sketch. So here we can see the LFSR begins, and every second it's going to work through that LFSR program and output the result of the LFSR. So I just wanted to show you that quickly. That's the standard Arduino way to implement this. And what that's doing in software, as the Arduino IDE compiles that code, it's going to generate the assembly code for that function, and that the assembly code for this LFSR logic looks like this code on the right side of the screen. It ends up being 22 instructions to generate the next number. So that every time you call that function, it steps through these 22 instructions. So I just wanted to demonstrate that and keep that in mind as we go through the rest of this example. So next we're going to look at the hardware implementation for the LFSR. So I'm going to pull up the RTL for the LFSR module, and I'll actually pull that up here in Quartus. So this file is found in the RTL directory of the XLR8 LFSR library. So this here is the totality of the LFSR module. Things to note, we have a new seed signal, an enable signal that controls the flow of the LFSR. So when a new seed comes in, it's going to replace the existing seed with that new seed. And the LFSR is going to advance with that same logic. Here's that same logic that we saw in software, where the feedback bit is the result of the XNOR of bits 7, 5, 4, and 3 of the LFSR data register. And every time the clock ticks and the LFSR is enabled, it's going to calculate the next state of the LFSR. And one more feature that we have in here is there's a heartbeat signal as an output for the LFSR, and all that is a signal that just toggles high and low just to show you that the LFSR is moving. So the next thing you want to do is instantiate the source code for our LFSR in our XLR8 wrapper file. And so that's this step here where we have this XLR8 wrapper in the LFSR example. The XLR8 wrapper is called XLR8 LFSR, and all it does is instantiate the LFSR logic and implements the registers for the design. So the LFSR contains 3 registers that control the LFSR. There's the LFSR control register, and all that consists of is 2 bits that users can control the LFSR with. They can set the LFSR into free running mode so that the LFSR will update as fast as it can with every clock tick. If it's not in free running mode, the LFSR is going to advance every time the LFSR data register is read. There's also a heartbeat bit that controls whether or not the heartbeat signal happens at a long interval or a short interval, and that's useful with the free running mode. So the default behavior for the heartbeat is to toggle every 10 advancements of the LFSR. Now, if the clock is running at its full 16 megahertz, a user would never, you would never see the heartbeat toggle. That's not very useful. So there's by setting that long heartbeat bit in the LFSR control, you can see the heartbeat toggle every 10 million cycles instead. Now there's also an LFSR seed register, and that register is how the user can write an initial seed state for the LFSR to get the LFSR to start from wherever you want it. And then the LFSR data register is going to be the resulting output of the LFSR module. So just keep in mind that these 3 registers are being used by the design, and we're defining the different addresses for those 3 registers. So next we're going to take a look at the XLR8 wrapper module, and I'm going to pass the control back to Steve for this part.
Thanks, Brian. I just want to go back one slide and just make a comment. When we're talking about that we're defining these registers, when we talk about the LFSR logic, the custom logic, and the register definitions, this is an example of what a user might do. So it's not us as the Lorian that's defining these, it's whoever's writing this custom logic. They would also define these registers for themselves as far as what the functionality of those registers are, how many there are, what addresses they go out. That's all something that the user does, and they're able to do anything they want there. So now let's look at the wrapper module itself. As I said earlier, this module is intended to add an interface to the configuration register data bus. So we'll be renaming it now to XLR8 LFSR, and then instantiating our module in there. And I'll just go look at the code itself here by bringing up Quartus. So you can see right at the top here, we've defined a couple of parameters, 3 parameters that hold the values for our address. They default to 0, but when we instantiate this, we'll specify something else there. And then in our input-output list here, you can see most of these are our standard data bus signals for the configuration data bus, which by shorthand we just call the D-bus. There's also the some signals for what we're defining for LFSR here. I'm just going to scroll down just a little bit here. Not sure how that translates on the webinar, but this logic here is somewhat boilerplate. For each of the configuration registers, there's 3 of these equations. We create a select, a write enable, and a read enable signal for each of those registers using the standard logic here. And each of those has its own parameter, the control address here, the seed address here, the data address here that correspond to the registers that we're talking about. Next, we need to, on the output side, creating the data bus going out and the output enable signal that goes with it, we need to combine together the data coming from the 3 different registers. That's what's happening here. And then for each of the registers, the configuration registers, we have a little bit of control logic. For instance, for LFSR control register, we have this logic, which on reset clears the register, all zeros. But otherwise, if we're not in reset, then whenever we have a control write enable signal, we parallel load the LFSR control register from the D-bus input. There's similar logic here for the LFSR seed, where it gets cleared on reset and loaded when we have a seed write enable. And we're also loading the seed write enable into another register that we're calling the new seed. That's not a configuration register, it's just a holding register so that we can line up the data in LFSR seed register with the write enable signal that's going to go into our instantiation. Scrolling a little bit more now here, we can see the instantiation of our custom logic right here and the assignment of signals into it. And we can see that we're using bit 0 of the control register going into the enable input, and we're using bit 1 of the control register going into our long_HB input. We can see our outputs, our heartbeat signal coming out, and LFSR data coming out. That's actually also one of our configuration registers. So in this case, that configuration register is actually living inside of our custom logic, but it's still addressable via the configuration data bus. Let's go back to our presentation now. So now, having wrapped our logic in the wrapper template, we're going to instantiate it in the OpenXLR8.v file. Now, as I mentioned earlier, the OpenXLR8.v file is the top level module, and it gets instantiated at the top level of the FPGA logic and communicates directly with the AVR core, with the input and output pins, with the interrupt logic. It provides access to all of that stuff to the user's logic that lives inside of the OpenXLR8 module. So you can communicate with the input and output pins and interrupts and the core itself. I'm going to bring up Quartus again now to look at the actual code for that. The OpenXLR8.v is a little bit longer file, and that's mostly because we've added many, many comments to make the file self-documenting. So don't get too intimidated by the length of the file here. Most of it is just comments. I call it the wall of green because comments are green. Here in the header, we can see that there's basically 6 sections of this file that contain the various pieces that we are concerned with. The first section is going to define our input parameters and input and output signals. Here we're actually including a file that defines those. We store that over in Accelerate Core so that we can easily update that if we decide we're going to add a new signal to the OpenXLR8 module without having to go out and modify every existing OpenXLR8 implementation. But we do in the comments here have a copy of the current contents of that file for reference. And you can see parameters being defined here at the top. We got our design config, which is used during compilation to specify what type of image we're building, since there are different size FPGAs and there are different boards that have different features. We've got the num pins, which tells us how many pins we have on our board that we'll be able to access. For the Uno board or for the Accelerate board, it's 20. It's more for the Snō or the hinge. And then we've got some other parameters that allow us to communicate with our interrupt logic within here. Here's the inputs and outputs to the module itself. We've got clock and reset as normal. We've got a number of different clocks that are available for the user logic so that you don't have to run at the core clock rate that the rest of the FPGA is running at. You can use faster clocks. We provide the 16, 32, and 64 megahertz clocks as standard. And there's also a couple of optional clocks where the user can specify those clock rates and then use them within their own logic here. So you can run the OpenXLR8 modules at faster clock rates than the rest of the FPGA. The enable clocks here, really these are more like heartbeat signals that are used for timers, kind of giving you a little bit longer duration heartbeat signals. These signals here are the standard data bus, D-bus interface signals coming into OpenXLR8. The other section here contains the GPRF, which is actually a copy of the AVR register file in its entirety. So that's available for the OpenXLR8 users to read values directly out of the register file. So rather than having to use an I/O operation to transfer a value from the register file out to the OpenXLR8, the modules in OpenXLR8 can read those directly. There is no write access, though, to that. It's just read. XB pin X is a copy of the values of the input pins. This is how the OpenXLR8 modules read values off of the pins. And then these JT signals are the JTAG pins on the board. These pins are not normally used during normal operations, so we make them available for OpenXLR8 users if they want to use them for something else. These next 4 buses are used for controlling the output pins, and we'll get into the details of that in a bit. And the final one here is our interrupt signal going back to the core. Scrolling a little bit here. This next section is where we define our signals that we use within the module. Again, here's some that are used for controlling outputs, and those are standard and don't need to be modified by users. We'll get to that in a second. And then for signals that are unique to whatever implementation of OpenXLR8 we have, we would define those here. Here you can see we've defined a couple of signals for our LFSR implementation. Scrolling again, and here's our implementation or our instantiation of the LFSR wrapped module. And you can see we're feeding in at this point the addresses that we're going to use within there. So you might recall we set those to default value of 0 in the actual wrapper, but here we're feeding in the values we'll actually use. And the signals going in and out of the LFSR are mostly the standard D-bus, but you can see we are also feeding in these heartbeat signals, and we've got some outputs for like the D-bus out and whatnot. So now we get to our output control. This is a little bit more complicated than one might think. The reason for that is that we're following the standard that's defined in the AVR architecture spec. In that spec, they use 4 different signals to control each output pin. Essentially, there's 2 that are called the DD signals. Those control whether we're going to actually be controlling that pin, and if so, how we're controlling it. So the DDoE signal here is used to say whether we're going to control the pin or not. If we set that to a 1, that means that this signal is going to control that output. And then we can use the DDoV signal to determine whether that pin is going to be an input or an output. If it's a 0, it's an input. If we set it to a 1, it's an output. In the case where we set it to be an input, the other 2 signals don't really matter, they're ignored. But if we set DDoV to a 1 and we're using it as an output, then at that point the PV signals come into play. PVOE is used now to turn on that output. The output enable signal controls whether it's actually active or not. And if it is active, then the PVOV signal will specify the value that goes on that pin. So now if I scroll down a little bit more here, you can see in these assignments that we're specifying values for pin 2 and pin 13. In the case of pin 2, that is going to be an input. and it's going to be a signal that eventually will control pin 13. But since it's an input and we want to control it, we're going to set DDOE to a 1, saying we want to control this pin, and then we're going to set DDOV to a 0, indicating that it should be an input. For pin 13, we want that to be an output. Pin 13 actually controls the LED on the board. So we want it to be an output, so we say, yes, we want to control it, so we set DDOE to a 1. We want it to be an output, so we set DDOV to a 1. Then we're going to use the output enable of that and use the actual input signal on pin 2 to control the output enable of pin 13. So if pin 2 is a 0, then the output will be enabled in this case. And if it is enabled, then we're going to put our LFSR heartbeat signal onto that output. So as I said, it's a little more complex, but it provides ultimate control over those outputs.
And as you said, Steve, this is basically all because we wanted to maintain, compatibility with the AVR architecture, right? We're just following along those lines.
Exactly. You can look this up in the AVR architecture spec, and it lays out these signals just as I've described them. Scrolling down a little bit more here. Here we have some standard logic that, as it says, do not edit below these lines. This is in the case when you have multiple modules instantiated within the OpenXLR8. Perhaps you have different blocks that are communicating with each other and using different pins. We need to combine their control into a single bus on the way out, and that's what this logic does. A little bit further down, for the output related to the D bus, we need to combine outputs of multiple blocks if they exist. In our case, we only have one block, the LFSR, so we just use the LFSR D bus out and the output enable directly. If we had more, as you can see directly above here, this is the case where if you had 3 different modules, you would have 3 different D bus outs and 3 different enables, and we just combine them as shown there. And the final section is for inputs. Our LFSR example does not use any interrupts, so we just set that value to a 0. But if you did need to use interrupts, we have a module that we include. It's called the Accelerate PC Int, and that provides the interface that we need to the interrupt logic of the AVR core itself.
And Steve, one of the things that I was going to share at the end as well is that we've got some plans for some upcoming webinars in addition to this one. This is the intro level, but we also are going to be doing sort of an advanced OpenXLR8 down the road, right? Where some of the things we're going to talk about there would include things like if we're going to use interrupts, how do you use that? How do you use our interrupt block? How do you maybe stitch together multiple XBs? And we would cover that kind of material in that advanced OpenXLR8 webinar. Is that correct?
Yep. Yeah, we just don't have time in the scope of this workshop to do that.
Right. Understood.
We'll cover these things in other videos.
Great. Yep. I just want everybody to know that we do want people to understand that we're going to be putting some additional content together as we get into more complexity of how you might want to stitch things together. We do plan on doing some subsequent webinars that get into that level of detail as well.
Yep. Absolutely. So now we've got all of our source code modified and put together. Now we're going to modify our XB address pack file to specify those register addresses that we've been talking about. So this address pack allows us to define values for some parameters that are used then in the logic. So these 3 lines here, where's my cursor? There we go. These 3 lines here, these names should look familiar. We just saw those in the code a minute ago. And now we're assigning values, in this case, E0, E1, and E2 as addresses for those registers. This file also is kind of a wall of green. There's a lot of comments. We can't show them all here because there's so many, but basically for all the available address space, we list which addresses are available for use in OpenXLR8 and which are not. There are some addresses that are used by the AVR core. There are some that are used by Snō or Hinge in those cases, since they have additional features beyond what the standard AVR does. And so in those cases, they use some additional addresses. but it just indicates in there which addresses you can use and not use. There are many, many addresses available, so no one should have a problem running out of addresses. So now we're done over in our RTL directory. We're going to go over to the Quartus directory now and modify the OpenXLR8.qsf file. So the OpenXLR8.qsf file is a Quartus settings file, and it allows a user to set any Quartus settings that they would want to do for their design. Mostly what that consists of, as shown here, is a couple of statements that just tell Quartus where to find our custom logic source files. The Alorium LFSR.v and XLR8 LFSR.v. Those are the new ones that we created. The OpenXLR8.v, for instance, the other scripts already know all about that, so you don't have to specify that. You just have to specify the ones that are newly created for this particular OpenXLR8 implementation. So now we've got all our files modified, and we're now ready to launch Quartus and actually start building something. And I'm going to hand it back over to Brian at this point and let him run you through that part.
Okay, so we are actually going to open up Quartus now, and we're going to be taking our entire design, load it into Quartus, and generate the RPD file that we need to burn to our board. So in Quartus, and I actually have the project open right now, so I'll just kick that out. But you actually want to go into Quartus and go down to File and Open Project. You're going to want to find the build directory, and that's already open here, but it's in your Arduino libraries directory, and then in the Accelerate build, we go into extras and Quartus there, and then we're going to, we have these 3 different project files that we can open depending on which board you're targeting. And we're actually building for the Accelerate Snō today, so I'm going to open the Snō QPF file, and it takes just a moment to load that.
While that's loading, Brian, I'm going to throw another poll up here real quick.
Sure.
If that's all right. Just out of curiosity, because I've had this question come up in terms of design entry, and I'm just curious. You know, we tend to be a Verilog house here. We've got a long history of that, and all the stuff we've designed so far has been in Verilog. Now we know we have a lot of users out there that use VHDL as well, particularly with FPGAs, and if you kind of come out of a government or some of the industrial sectors, and we know we can do some co-simulation and co-synthesis of those languages. So just wanted to get a feel for that as we're looking at how we build things out going forward or what we're doing in the future. It's good to know what people are using. So if you guys could take a quick look and let me know, is it Verilog VHDL, or are you doing something different? We are also looking at some of the high-level synthesis techniques and tools that are out there in terms of being able to maybe enable our customers to write some of their design code potentially in C, and then take advantage of some HLS tools to convert that to RTL that could be used on here as well. That's quite a ways out. We haven't actually taken any tangible steps there yet, but that's something that's very interesting. So anyway, just wanted to throw this poll up here. So far, of the few people that have answered, it looks like VHDL is currently in the lead. Give just a couple more seconds here for people to take a look and share your thoughts, and I'll end it and share the results here. Oh, come on. It's neck and neck almost, Verilog and VHDL. Anybody else? Anybody else? I should have thrown Emacs versus Vi up here too. Then we'd get people involved. I wouldn't want to add a free comment section there though. Oh, I'm tempted to stop it now at 50-50. 6 of 9 have reported so far, but I want to let Brian get rolling here. So, all right, well, I'm going to end it and I'll share the results with you. So we ended up at 3-3 Verilog versus VHDL, but I will say that the VHDL advocates answered first and most emphatically. So that's probably the most popular right now among the crew. But anyway, thanks for sharing. All right, Brian, sorry to interrupt you, but go ahead and get rolling.
All right. So the other setting that you want to take note of is our Accelerate board. You actually can build targeting a 16 megahertz clock, a 32 megahertz clock, or a 64 megahertz clock. So the default is always to build for 16 megahertz, but we do offer those two other speeds. Today we're building for the 16 megahertz. But you can find that in this drop-down menu up there. So the next thing to do is to compile the design, and you can do that by, you actually just go to Processing, Start Compilation, or simply click, there's a blue triangle icon in Quartus, and it takes about 10 or so minutes to do that. So I'm not going to be doing that today. I've already compiled the design for us, but all you do to start compilation is just click on this blue arrow here. So once you've compiled your design, which I have, you want to convert the compiled design to RPD format, and the tool for that is built right into Quartus as well. So after compilation is complete, you just click on File, Convert Programming Files, and open up your conversion setup file. So I'll show that here in Quartus. Clicking on File, and then down to Convert Programming Files. That'll open up this dialog window here. Then you want to open your conversion setup data. And it's going to open the Quartus directory again, and there's different conversion files for each of the different possible board and clock combinations. So again, we're building for the Snō today at 16 megahertz. So I'll just, I'm going to open this conversion file here. And then down at the bottom of this dialog window, just click on Generate. And because I've already created it, I get some warnings, but it just takes a moment and it's going to generate the output files for Snō at 16 megahertz. And then you can close this dialog window. So the last thing to do is to launch the Arduino IDE and load the RPD that we've built to our Accelerate board. So we're going to upload our design to the FPGA now. So to do that, we've actually built the tool right into the Arduino IDE as long as you have our board tools installed. So I'm going to go ahead and open up the Arduino IDE now. And you'll find the here under Tools on the Arduino menu. You want to go down to the board selection here, and then roll down until you find our Alorium Accelerate boards. And again, today we're building for the OpenXLR8 Snō. So you just select the OpenXLR8 Snō as your option here. Then you want to make sure that your port is selected. I've got my board plugged in here, and it shows up as COM16 on Windows. The rest of these settings don't matter for burning the RPD image. But once you have that selected, the last thing you do is you click on Burn Bootloader. And again, I'm not going to be doing that today. I've already finished the exercise here. It takes about 2 minutes or so to do that, but you just click on Burn Bootloader, and after a couple minutes, the board is going to have your image on it.
And if anyone's interested in seeing that process, we do have a demonstration video on our website of how to run that Burn Bootloader. It's not for one of the OpenXLR8 images. I think it's like switching back and forth between 16 and 32 megahertz or something. But that if you want to kind of see the type of output you'd get and how to check it using one of the Get Accelerate version sketches that we have to verify that it changed, those videos and demonstrations of how to do that are on our YouTube channel.
So now that the Accelerate board has our new image on it, we're going to show what we've done now. So For the LFSR, I've written an Accelerate LFSR header file. It's just a simple little class that handles the register access for the LFSR, and that's really all it's doing, is just accessing those registers. So you can see the registers are defined up here at the top of the file. There's the control, seed, and data registers, and the addresses of those registers match exactly what we defined them as in the RTL. And there's just, you can set the seed and you can get the result of the LFSR, and you can control the bits in the control register. So that's really all the software layer is doing to talk to that, the RTL burned onto the board now. So I'm actually going to load up the an example now so that we can see the LFSR running in the RTL. So this is very similar to the software solution that we saw at the beginning of the presentation, but you can see there's no software function running to calculate the LFSR anymore. All we're doing is setting up the initial settings of the LFSR registers in the RTL, and then simply querying the LFSR data register and printing it out to the screen. So with my Accelerate plugged in, I'm going to write this sketch to my board. And I'll open up the serial monitor so that we can see the resulting output. Okay, so again, this is the same sort of logic running on the RTL on the Accelerate board now. So let's talk about what we've gained by doing this. If you remember at the beginning of the...
Brian,
yep,
just a comment there.
Oh, yeah.
You might have noticed that the values were printing out every 1 second.
Yes.
So
and
even though we've accelerated the LFSR function, the rate that those come out is still controlled by a wait 1 second command in the software. So
exactly, yeah.
it's not reflecting any speed up yet.
Right, this delay that I have here is just telling the program to wait for 1 second between each print, and it's going to get a new version of the LFSR each time that it reads from the data register. So again, from the beginning of the presentation, we had the assembly code that was generated for the software solution for the LFSR logic. That was 22 instructions that were executed every time we generated the new LFSR. And then with the RTL solution, we actually have reduced that down to a single instruction where all we're doing is reading the value of the data register. So this is the difference that we're talking about between software and RTL solution. So that brings us to the end of our presentation here today, I think.
Yeah, I did want to share real quick, Brian, before we jump into Q&A,
Sure.
if you don't mind me sharing here. So I mentioned a few minutes ago that we have some upcoming webinars that we're going to focus on and we're going to offer. And there's kind of two of them that we've got on our minds and that we've been sort of putting things together for. One is an advanced OpenXLR8. And in this one, we want to get into a little bit more of some of the RTL design considerations, maybe talk a little bit more about how to think through your RTL design and some of the things you might want to do there, and get into using interrupts, as Steve talked about when he was looking at that one block that had the big interrupt control logic in it. There's some unique things that you need to think through with using interrupts and how to use that block, and particularly if you're using multiple interrupts, and ways that we've tried to make that useful to you, as well as some advanced clocking techniques. And right now, we are just using basically the standard 16 megahertz clock that we're just running the Arduino on, or the ABR. But the chip is obviously capable of doing more than that. And we've got some examples. We've got some stuff that some of our engineers here are working on, where they're running the clock a lot faster to power their logic but we're still running, the interface and things like that for the AVR at that 16 megahertz. So we can get into some of that. The other one we want to do is one that we call OpenXLR8 with off-the-shelf XBs. And the idea here is, we offer a handful of accelerator blocks that we just make available. And this webinar is really kind of taking a look at, well, let's say you have just something custom you want to put on. How do you put it in there? How do you stitch the logic around it? But if you want to take advantage, let's say you had some custom secret sauce you want to design, but you want to take advantage of our servo block and our quadrature block and some other things that we make available to you, we just kind of want to dive into that a little bit and say, well, how do you do that? What's the best way to take advantage of the blocks we make available? And what's the most efficient way to do that and stitch it into your design? So those are two additional webinars that we've got that we're putting together. Dates are still to be determined on those yet. We'll definitely announce those via email or social media. If you aren't currently on our email list, I encourage you can go to loriumtech.com/subscribe. We do a really good job of not spamming your inbox and just, harassing you, but we do want to get information like this out or anything new and exciting that's going on. We do tend to keep you updated there, but I try to be pretty quiet and conscious of your inbox. So I just wanted to share that before we step into Q&A. So, all right, it's a good time to open up some Q&A. If you want to either type them or if you have a question you just want to ask live, hit your little raise hand there and we can just unmute you from this side and allow you to ask questions directly. We don't have a huge number of people here, so if you're interested in talking live, that would be great. I'm not seeing too many questions come across. I know I'm seeing some familiar faces on the webinar that have been on here before in the past. And I think, as Steve said, some of those files we have, they're full of a lot of comments. We really are trying to do the best we can to self-document those files. So as you're working your way through those, you can understand sort of what the intent is and where your logic goes and the kind of changes that you have to make. What I would request is if you are doing this or if you're trying, if there's anything that just doesn't seem to make sense or you wish was explained better, please feel free to be very bold in letting us know. As you guys are all aware, it's very easy to look at something and something seems really obvious when you're the designer, but it's not so obvious when you're trying to get other people to understand it. So we would love your feedback as you're looking at it. We really are trying to create an environment where you can design your own logic and then take advantage of the platforms we've created, the hardware we've created and easily get your code on there, integrating and working with the AVR microcontroller that's on the chip. Any other comments, Steve or Brian, from your side? We got a pretty quiet bunch. Oh, it looks like we do have a question.
I'll make a comment. We demonstrated here with a very simple example, the LFSR, and we saw basically a 22x speed up on that function. But that's a very simple example, and there's a lot more you can do with hardware. Essentially, it allows you to do almost anything you want. One could imagine scenarios, for instance, where you were in an IoT environment and you had a lot of sensors that you needed to monitor. One could write a module in OpenXLR8 that monitors, say, 8 or 16 different sensors and have it operate essentially autonomously from the AVR, completely isolating that, and just have that hardware sensor interface looking for things that might be interesting that are happening on those sensors and then only interrupting the AVR processor when that happens. That completely offloads that functionality from the AVR, so the AVR can be doing other things rather than constantly checking each individual sensor to see what its status is. So there's a lot of additional things you can do in hardware beyond this very simple rudimentary example.
Yeah, that's a good point. And we, in fact, have customers that are doing that exact thing. And because you can parallelize so much, it makes it a great way to be able to just read data in or do control stuff. And like you said, Steve, once things are kind of set up, it just sort of runs all by itself and really doesn't need to bother the AVR at all.
Right. And it allows you to run things on an AVR-based device that you wouldn't think you would be able to, just because it doesn't have as much processing power as you might think you need. But by offloading to the hardware, you reduce the computational need that much.
Yeah, that's a good point. So we got a question about how to set up the Arduino IDE. And that's actually something we didn't go over in this particular webinar, Fabio, but that is something that there's a couple places you can get that information. One is we do have a quick start guide out on our website that I just posted in the answers for that. So if you go out there, you can take a look, and there's a pretty clear step-by-step guide of how to set up the Arduino IDE. We also have a demo video out there on our YouTube channel for that. It's really simple. The thing that's cool about what we've done with our boards is that just out of the box, or as soon as you get them, you can just use it essentially as an Arduino board. So if you were to take, for example, XLR8, and you just open up Arduino, if you've downloaded that from the Arduino website, you could plug it in. You could just tell it it's an Arduino Uno, and it'll work. You can write your sketches for it. It'll just work like that. If you want to take advantage of the accelerator blocks that we've got built onto the board when you get it, or you want to do any of this OpenXLR8 stuff, we do have board packages and libraries you can download. And the path that you have to enter into the setup stuff and the settings for Arduino IDE is on that startup page that I sent you. And so that'll have everything you need to get it up and going. All right. Well, we won't hold you guys around here unnecessarily. I want to say thank you very much for coming to check things out. If you have additional questions, just head over to our website and shoot us an email. You can contact us in a couple of different ways. We'd love to hear from you. And if there's anything you need help with, please let us know. Or if there's anything we should be doing differently or offering that we're not, please let us know that too, because we really do want to continue to build on this platform and help you guys take some next steps here. So Donna asked, what is the max clock speed on the FPGA logic? Steve, I'll let you address that one.
Well, we support 16 and 32. We also have 64. That's not officially supported. It does work in all the cases that we've tried it, but there's sometimes compilation timing errors when you run at that rate.
And that you're talking about the images we put out that with the AVR speeds, right? But is there a case where you could do some custom clocking where you might be able to clock a custom block at something faster than that, even though the AVR might still be running at 16 or 32?
Yes. Using those two optional clocks that I mentioned when we were looking at the OpenXLR8 module, the user can specify different clocks by reconfiguring the PLL through another file that's included there. It's pretty simple to do. It's not covered in this tutorial, but you can specify faster clock rates and then use them within your OpenXLR8 logic.
Do you know what this particular Max 10 is capable of? I mean, theoretically, I don't know off the top of my head.
I don't know either off the top of my head.
Okay. But certainly we know that we could go, I mean, the FPGA itself supports well beyond 32 and 64 megahertz. It's just that when it comes to what we can do with the AVR logic itself, that's where we limit things. We came out of the gate with it running at 16 megahertz just because we wanted to ensure it was compatible with any of the libraries and code and things that are out there. Some people who have implemented libraries for Arduino get into some pretty low-level stuff where they have timing expectations because they're just expecting it to be running at 16 megahertz. And we really wanted our customers to be able to just use it and not run into those kinds of problems. As Steve said, we formally have released 16 and 32 megahertz cores. We've also sort of unofficially released a 16 or a 64 megahertz core that we have a couple of customers using. And that works. So far, it seems to be working for them. As Steve said, when you look at the output out of Quartus will actually tell you there's some timing violations, but we haven't seemed to see it make anything fail yet. So John, your question about user-developed Accelerate modules, that's something that we've talked about in trying to put together some kind of a library. So the question is there going to be a mechanism for accepting user-developed Accelerate blocks and making them available? We've kind of talked about trying to do some kind of library or something like that. We don't really have anything firm or specific in mind there, but we would love to see some kind of community-generated XB environment created. And I don't know, Steve or Brian, if you have any thoughts on that. This is a conversation we've had internally a little bit.
Right, and we you can access our Accelerate reconfig script to actually write an RPD file. So if you were to generate an RPD file, you would be able to share that with somebody else, and they would be able to burn it onto their board. But so far we don't have a mechanism where we like have a server space for users to upload that to and then share it with other people. So
I think we've talked about creating a GitHub repo that anyone could write to upload their unique libraries, OpenXLR libraries to, so that other people could download them from there.
Okay. Well, looks like we did get you guys out of here in shorter than 90 minutes. So that's a good thing. Thank you so much again for hanging out with us. And everybody have a great afternoon, and keep your eyes on your inbox. If you're on our email list, we'll let you know when those other webinars are going to be happening. Hopefully we'll get a chance to interact with you down the road. So thanks for joining. Thank you, Steve and Brian and Harley, for kind of running things in the background for us and for doing the presentation. Randy asked, will the webinar be available on your website? Yes, it will, Randy. Usually it takes about a week or so. We just kind of want to get the video and audio edited, and sometimes we need a little bit of cleanup, but we will get it out there and let you know when that stuff is ready. Okay. Thanks all from our side and for our attendees. Really appreciate it. Have a great afternoon.